Okay, good morning, everybody. Just want to remind people about the extra examples I put up online for you guys. If you go to the browser, just want to remind you that there's some good stuff there for you to review. Extra examples that we looked at. And okay, let's see if we can get there. Here we go. Right, we put these last sequences, series, and comparison tests, limit comparison test examples this weekend. Hopefully, you guys got to some of those and gave you some nice, very good examples to look at and study. So, it's working out kind of well, I guess. But anyway, today what we're going to work on is another technique, and it's called the alternating series test. So we're going to go to the iPad Pro here. Okay. Alternating series test. So, of course, it's going to be based on some assumptions. I want you guys to note a few things. So far, with the last test, our terms were positive terms. And so far, or at least with that last test, they gave you things like this. Okay, you got some AN where your AIs, and we say that for all I, and that just really means I goes from 1 to n, that these terms so far have all been, positive. So, okay, so we're looking at these terms here. Now, when they say alternating series now, right, alternating series, of course, this is going to change. This is going to now alternate from positive to negative, or really negative to positive. The point is that it alternates, and they mean alternate sign. So when you say alternating series, well, the sign alternates. And so the assumptions that you have now for these terms, these AI for all I here, are no longer that it's simply positive. Okay, so these terms are going to alternate between plus or minus. Now, what that means is we have to have an alternating mechanism, right? So let me remark here about those things. So let's take a look and summarize these alternating mechanisms. Really, it looks like this, right? Negative 1 to the nth power. You can have negative 1 to the n plus 1 power. I've seen negative 1 to the n minus 1 power. And I've actually seen cosine n pi. And these are all the alternating mechanisms that are out there. And they're going to be in your series. So you'll see something like this. Negative 1 to the n minus 1 over maybe n. And you could say this starts from 1, or starts at 1, to infinity. And so now n is 1. So you have, okay, this is going to be negative 1 to the 0 over 1 plus a negative 1 to the, now this happens when n here is 1. N will be 2. N will be 3. So we see n is 2. This will be the first power now. And this is 2 plus negative 1 squared. And this is 3. And then this goes on forever. And so when you look at this, you might say, what does this really look like? Right? Well, these terms here, this is 1. That's really negative 1. Negative 1 squared is 1. And so negative 1 cubed, the next term will be negative 1. So you're starting to see how this really behaves. This behaves as 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. And as you can see, we alternate in sign, and there's a positive sign there, right? And so this is an alternating series. Okay, so here's something that you can see. And again, you might say, well, what's the point of this particular test? Well, this test applies to every alternating series. So let me write down here the alternating series test. And of course, we have some assumptions. And it looks like this. They're going to write it this way. They're going to say, if this series, they're going to have Bn there. Or actually, they're going to have it like this. I think your book writes it as -1 to the n minus 1 power, and then that's a b to the n. And I just want to point out to you that altogether, I guess you can think of this whole thing as an, but okay. And this series will look like b1 minus b2 plus b3 minus b4 plus, and again, the point is the terms will be alternating in sign. And it starts there with a plus. So you have what's called an alternating series. So they're saying if you have an alternating series here and it satisfies, these are the additional assumptions. That the Bn portion has to be decreasing. Okay, so it has to be decreasing, and your book gives you sort of a definition, and it's kind of like saying Bn plus 1 is supposed to be getting smaller, right, for all n. And so you have a decreasing Bn term. They're talking this portion. So Bn has to be decreasing. That's our first set of assumptions. The second assumption is that if the limit now, as n goes to infinity, for Bn, that has to equal 0. So if we have these two things satisfied, if we have them, then we can say the alternating series described the way they gave us converges, is finite. And that's the alternating series test. So we need to satisfy two things. The Bn portion has to be decreasing, and really the big deal is that the limit here has to be 0. So if you show those two things, then we have a convergent alternating series. And this is called the alternating series test. I abbreviate it, and you'll see me abbreviate it as AST for short. So here's our alternating series. Now, if we go back to that first example here, and you say, okay, this is a series they gave us. Notice what Bn is. Bn does not include the alternating mechanism. So I'm gonna color this red here, and I'm gonna say this is the alternating mechanism. So when you actually use this test, if we go back up here, our Bn now is going to be really 1 over n. Because what I remove here is the alternating mechanism, and this is that Bn term in the alternating series test. So this is what we're going to look at. This is what we really analyze, if you want to call it that, in terms of two things. This thing needs to be decreasing, and it is. And we need to show what the limit is as n goes to infinity. So Bn here being 1 over n is a decreasing sequence, meaning you start with 1 and the next term's 1/2. That got smaller. The next term is 1/3. It's getting smaller. The next term's 1/4, so it's strictly decreasing. Okay, so we know we have the decreasing portion satisfied. So if you said, well, what happens with this limit of that Bn? And I'll write it down, so you can see every detail. That limit of Bn now, well, this is 0. So this limit is 0. Now, you say, why is that important? Well, because by the alternating series test, and here's what we get to say now. By the alternating series tests, the original series they gave us converges, right? That's finite. So that's a quick illustration of, what we're working on today, these alternating series, and when are they convergent? So we know that this is actually a convergent series. So, okay, let's emphasize that. It's finite. So let's look at some more examples of the alternating series test. Let's say, for example, we have, they might do something like this again and give you something and say, okay, you have 1 over the square root of 2 minus 1 over the square root of 3 plus 1 over the square root of 4 minus 1 over the square root of 5 plus, so they describe our series, and they want to know about convergence or divergence. So with this here, we know, okay, we can describe this series as, first of all, you have 1 over the square root of, it starts here at 2, so I'm going to still put n, but I'm going to say start here at 2. Okay, it doesn't matter if it starts at 1, it could start at 2. But I have to be careful with the alternating mechanism. See, if I start with n is 2, the question is, when I use this alternating mechanism, I have some choices here, right? So remember, we have -1 to the n, -1 to the n plus 1, and really there's only 2 choices, because -1 to the n minus 1 would be equivalent to, the one I just wrote down. So these two are about the same depending on n. Anyway, and then of course you have the cosine n pi. So I just want to make sure that when n is 2, I start with a positive term, because this is positive. And then when this is going to be when n is 2, we don't have to start with n as 1. The next term has to be negative. So which one of these does the job? It looks like this one will do the job, and really, with n is 2, we get -1 squared, 3, 2 minus 1. This does the job here, so this is the one we use. And this is why I put originally -1 to the n. So the series here, to describe this properly, alternating, if we start with 2, and we're a little bit more sophisticated with these now that we've had all this experience, this is what they're talking about. This is the alternating series as they describe -1 to the n. Now, does it converge? Well, we have to consider, what is Bn, right? Because this whole thing here is An. But this portion here, that's going to be your Bn. So since I know Bn here is 1 over the square root of n, Remember, this is decreasing. That means the terms are getting smaller. So when b is 1, this is 1. When b is 2, it's 1 over the square root of 2. When b is 3, it's 1 over the square root of 3. It's decreasing. We have to check the limit of bn. So our limit of 1 over the square root of n, as n gets big, we know this is also 0. So we satisfied the two criteria, decreasing, and the limit is 0. And so this means that this particular series converges by your alternating series test. So it converges. So here's another illustration of that test. Pretty good test. Okay. Let's see a few more. 1 to infinity, negative 1 to the n minus 1 over the natural log of n plus 4. Now, here, our bn is going to be 1 over the natural log of n plus 4. And here's our alternating mechanism. So maybe I just call that AM for alternating mechanism. So we have to see if Bn, which is 1 over the natural log of n plus 4 here, what we just wrote down, we have to see if this is actually decreasing, right? And there's a very simple way to see that this is decreasing. Notice something here. If the natural log function, by the way, so I want you guys to consider this. The natural log function is an increasing function. This is increasing. But if I write this as a reciprocal, right, 1 over the natural log then is actually decreasing. And it doesn't matter if I change the argument of the function to be x plus 4. It's the same situation. I have a decreasing function. And that's in terms of x, right? But if I change my domain to be natural numbers, it's still decreasing. So, you can kind of determine that just like you maybe did the others. Same thing is happening here. The denominator square root of n is increasing, but the ratio 1 over that is decreasing. Same thing with this n. N is increasing for the first example. But the reciprocal of that, 1 over n, is decreasing. So we do have the criteria being satisfied of being decreasing. We just have to check now the limit now. So the second thing we check, what's the limit of 1 over the natural log of n plus 4? Well, that's kind of the same argument. It's decreasing to 0. Because the denominator gets big without bound, right? So what we're saying here is that as n gets big, the natural log of n plus 4, well, let's step back a bit. As n gets big, n plus 4 gets big. And what that means is the natural log of n plus 4 is also getting big, which means the reciprocal goes to 0. So this is the limit argument that we've been working with. And anyway, it goes to 0. So we say again, since it's decreasing, goes to 0, this series converges. We say it'll converge by the alternating series test. And there you go. And let's compare this example to the next example, because it starts to bring, well, I guess I can say, yeah. Well, it's okay. We'll try this one too. All right, let's try it out. Doesn't matter. The more you guys see, the better. So I'll put this here. Square root of n cubed plus t. So in this case, this portion here is our bn. So we say bn is n over the square root of n cubed plus 2. And again, we have the alternating mechanism here. So it's an alternating series. Now, you may look at this and say, okay, Mr. Judge, is this decreasing, right? Because we have to show that this is decreasing here. You know, is it getting smaller? So one thing you could do is you consider this function here, x over the square root of x cubed plus 2. And you want to know if this is a decreasing function. What can happen is simply the following. Okay, so we have some decreasing functions here. Which you may need to do to show that this is decreasing is to use calculus 1. So if you're in a situation where you don't know that that's decreasing and you have to show that's decreasing, take a look at sign analysis on the first derivative. And you can see that it'll be decreasing. So I can say to you guys, you can investigate that. We're going to have a decreasing function. And now we look at the limit here after you know that's decreasing. N over square root n cubed plus 2. And so we now have to find that particular limit. All right, so you say, okay, how do we get this limit? This limit here, as n gets big, if you go back to calculus 1, well, there's a couple of, well, we could do a couple of things. Right? How do you show that that limit is actually going to, what that limit is? You got to go back to calculus 1, maybe. Well, let's try calculus 2. I don't know. Let's see something here. Infinity over infinity, right? And you go, oh, okay. Maybe I have to go to calculus and say, what's the limit as x gets big? X over the square root x cubed plus 2. And that is infinity over infinity. And so now by L'Hopital's rule, you could take that limit, and this is the derivative of the numerator over the derivative of the denominator. So let's put x cubed plus 2 to the 1/2. And that's going to be the limit now of 1 over, and now I have to take this limit, x cubed plus 2 to the minus 1/2, and you get 3x squared. And you go, oh no, this might be a problem. And so you have the limit here of, let's simplify this. This looks like it's going to be this. So we're going to take up here, this is going to be the square root here of x cubed plus 2 in my numerator. And you got 3/2, and that'll be a 2 up here now, and you got that 3x squared. And so if you said, okay, Mr. Judge, I'm going to try this out this way. And then you see, wow, you get this situation again. So maybe using this is not a very good idea, because if you start doing calculus with L'Hopital's rule, you're going to see that you have this going on. And so you might start to say, well, what do we do here with this particular question if not even L'Hopital's rule looks like we get progress, right? And here's what I'm going to go back. I'm going to say to you, you do have an indeterminate quotient. Try to think of that the way we've been thinking of this. You're going to divide every term by the highest power of the variable in the denominator. So this is something I think I would look at. Now, you say, does that mean that it's n cubed? Divide every term by n cubed? No. There's a radical here. So you're going to divide every term by the square root of n cubed. So here's what this looks like. So I have here the limit now, let's write it bigger, of n, and that's going to be over the square root of n cubed plus 2. So when I divide every term by the square root of n cubed, the square root of n cubed, just like from calculus 1, because you have the radical there. Let's see what this does for us. So algebraically, we get the limit n over n to the 3/2 over the cube root of n cubed plus 2 over that n cubed. And let's do some arithmetic. So it looks like 1 minus, we have n to the 1 minus 3/2 over here. And now you have the square root of 1 plus 2 over n cubed, which gives you the limit now of n to the minus 1/2 over the square root of 1 plus 2 over n cubed. So double check that arithmetic is okay. 1 minus 3/2 was going to be negative 1/2. And that now gives me the limit of 1 over the square root of n, square root of 1 plus 2 over n cubed. N goes to infinity. Okay, so I can look at this kind of a couple of ways. I can actually split this up and say that we have the limit of 1 over the square root of n times the limit of 1 over the square root of 1 plus 2 over n cubed. N gets big. N gets big. So that this portion here we know is 0, and this portion is 1. So what we have here is 0 times 1, and we've shown that that limit is actually 0 as well. So since it's decreasing and the limit is 0, okay, we can say by the alternating series test, we have convergence. And that is what this test looks like for you guys. And, you know, we do have some more to do. And to say, we have a question here. Question is, can we try something with a factorial? Well, for alternating series, I could double check the book, but I don't believe you're going to have factorial for alternating series. Okay, so that's an alternating series kind of question. There's not going to be these factorials here. Anyway, let's take a look at some other examples that are going to start to become interesting as you see these here. So, for example, okay, we could do, how about, yeah, let's do something interesting for you that you haven't seen yet for alternating series. Something like this. Negative 1 to the n, 3n over 4n minus 1. So this is something you haven't seen and you really need to be prepared for, because going back to the logic, let me read this alternating series test logically for you. You have an if-then statement. Okay, very often math students don't really remember or understand the meaning of if-then. Okay, believe it or not, it's a conditional. You have if P, then Q. And this is a good illustration of this. You see, if you have these assumptions satisfied, you're talking about the setting of an alternating series, it's decreasing, and that limit is 0, then you can conclude that the series converges. Now, people really will have an issue, and let me show you what I'm talking about. There's a fine line here with the logic. And in this example, we're going to see something here that's interesting that we haven't seen. You're going to see that this is our Bn portion. So Bn is 3n over 4n minus 1. That's the Bn portion here for us. What this means, since we have our alternating mechanism, if you said, is my Bn decreasing here? Is this a decreasing function? Well, again, if you like, you could use calculus, and we can say, if we consider, we start off by saying, Fn is 3n over 4n minus 1, which really means, writing this as a function, f of x is 3x over 4x minus 1, which you guys may know is that this function is equivalent to 3 over 4. Well, that might not help you. We could do a couple of things here. This helps you in some sense, but we can write this function this way. If you just divide. And remember your division algorithm here, that you have 3x divided by 4x. So if you have 3x over 4x, that gives you a nice 3/4. That goes up here. And now you multiply, and you say, does that give me 3x minus 3/4? And the answer is yes. Let's double check. Okay, now I subtract, and I simply get the constant 3/4. And now you say, well, what does that mean? Well, this is the quotient. Here's your remainder. Here's your divisor. So this function, f of x, is the equivalent of some constant here plus 3/4 over 4x minus 1. Now you might say, why are you looking at it this way? There's a couple of ways I can see. This is really, if we started to talk about, remember, down here, this is increasing. However, you have a numerator over an increasing function, which means that this portion is decreasing. So you guys know. And then the fact that you're adding a constant to it doesn't change anything. So this is a decreasing function. Now, if you like, simply use calculus. Right? F prime x, you can do sign analysis for that. And you could show that this portion is a decreasing function. Anyway, if you take a look at that limit now, and here's the interesting part. You get 3n over 4n minus 1 if we try to take this limit. And so when you take that limit, n goes to infinity, again, you divide by the variable with the highest power in the denominator via calculus 1. Here's what you get. 3n over n over 4n over n minus 1 over n, which is limit n gets big, 3 over 4 minus 1 over n. Now, here's the interesting part. This limit goes to 3/4. And this is not equal to 0. You see, if it were 0 by the alternating series test, what we would say is that we have convergence if it was equal to 0. But because it's not equal to 0, here's what I'm going to say to you. What can we conclude? And that's where we're really at here. This is a very good question. It's a very big deal. This is what we want to know. What does this mean? You cannot conclude that we have convergence. Just looking for the test. There we go. Because this is not equal to 0, you can't conclude we have convergence. However, logically, don't say divergence by default. Don't guess. You have to justify your answers. This is why I've been justifying and saying by the alternating series test or by, the limit comparison test if you looked at those videos. This is why I justify it, because we're going to get to a point where you have to, look at some series here and justify whether it converges or diverges. You have to know for a fact. It has to be airtight. It's not guessing. Converge, diverge. If you guess, you don't get credit. Right? So there's no guessing here. You have to show the work. So what I'm really getting at is we can't conclude by the alternating series test. So there's no conclusion by that test. Yes, it's decreasing, but this limit is not 0. What does that mean? No conclusion, really, by the specific test, by this test, AST. However, let's take a step back. One of the reasons why I keep going back every day to you guys, and if I go back to the browser and I say, take a look at these examples, right? The sequence examples, the series examples, the limit comparison examples, that this portion here has a lot of good information you need to answer questions on convergence. So hopefully you guys want to keep up with some of those additional examples because they're really, really good. The reason I bring this up is because I'm going to go back to the first or the second set on series. I want you guys to recall something here because this is very clever. The series they gave us, what was that? -1 to the n. I believe it's 3n over 4n minus 1. Yeah, I guess that's the original series here. And so what I'm going to do now is I'm going to look at all of this here, since remember, this whole thing is an. Let's change the color. Yeah. This whole thing, we're going to think of as an. And you say, well, why do I want to think of that one just as an? Because of the fact that what I know is that the limit as n gets big of an is the limit of -1 to the n, 3n over 4n minus 1. And if I ask you guys, what is this limit? In other words, here's my focus, is on an. I include the alternating mechanism. I'm looking at this series, this portion of it. What I know is that the alternating portion goes to plus or minus 1, but I also know that this portion here goes to 3/4, so that my limit is plus or minus 3/4. Now, this is a very big deal. And you say, why is that a big deal? Because I'm showing that the limit of an does not exist. Now, if you're up with your homework, and hopefully you are, right? Let's ask you guys, what does this particular mean? But more importantly, why? Right? What does it mean to show that the limit of an does not exist? Anybody have an idea? What does that mean for you? I'm looking for a conclusion. So if you're really up to date, you guys will know exactly what this means. Because here's what you really got to know. And it's linked to the alternating series test. Anybody know? Who's up to date? Now, remember, we can't guess. So, it diverges, but we can't guess. If you just put diverges, I have to mark it wrong. Because I'm going to put on the test, justify your answer. So you got to justify that. Why does it diverge? What's the justification? What am I looking for? Yes, absolutely. Here we go. We're looking for that statement. This diverges by the divergence test. So here's what you guys want to write down. It diverges by the test for divergence. Absolutely. Right? But let me remind you guys. Yeah, it diverges. But you want to put this portion right here. You just don't want to say diverge. Because it's kind of interesting that, when I've given these questions over the years in a Calculus 2 course, you can always tell, really, it's not that you can guess. It's either going to converge or diverge, and it's a 50-50 chance. So people guess. They go, oh, yeah, converges. Oh, yeah, no, diverges, whatever. No, that's not enough. You want to know the test. In other words, if you're using the alternating series test and you show convergence, that's what you say. Converges by the alternating series test. Converges by the limit comparison test, right? Well, this thing diverges by the test for divergence, which really means you have to remember that test, right? And you say, well, what was the test? You have to recall that, because that was a big deal. If the limit of an, remember those things? If the limit of an, you're going to have to say a couple of things. Go back to that test. So I want you guys to know. What is this? Because I know a portion of it says if the limit does not exist, that's only one portion, then we can say for certain that the series diverges. So you guys can go all the way back to something like that and take a look. But this is going to be a very, very powerful tool in your guys' lives here with this topic, that test for divergence. So you're going to see that come up more and more for you. Right? So go back and double check to make sure you know that test, because you're going to see rather quickly this week, oh, we're going to use that. I'm going to use that over and over again. It's going to creep up for us. So you want to know what that is. And, that was one of the most important things I think I ended on. We gave you that introductory to series, right? So you got to know, what is this? You got to know it. Well, the test for divergence is the following. If the limit of an is not 0 or does not exist, then the series an diverges. So there's a very big detail here that I'm looking at this whole thing as an. I'm not focusing at all on a bn. Okay, so this gives you a sort of logic to follow. This whole thing is your an, and you've shown that the limit goes to plus or minus 3/4, which does not exist. That limit doesn't exist. It goes to two values. Remember, it alternates between these two numbers forever as n gets big. So by the divergence test, this is the portion that says does not exist. Then we have divergence for this series an. Now go back to the alternating series test, because this is a big deal. Once you find out here, whenever you have a decreasing sequence, but the limit is not 0, it's finite, you can't say this diverges by the alternating series test, because the alternating series test doesn't have language of divergence. Okay? This is why I said we can't conclude by this AST. We can't conclude, get a highlight. We can't conclude by the alternating series test, because that limit doesn't go to 0. But if you look at this as a series as a whole with an, then we could use the fact that this goes to a finite number, even if that went to, goes to a finite value. We can still conclude that this series diverges by the alternating series test. And so this is kind of an interesting idea here. And they're linked together. But if we're clever and we notice that's a finite number, then we go, certainly not 0. We can't say anything by the alternating series test, meaning we can't conclude convergence, but we can use the test for divergence and say this diverges. Okay, now we have a question here. Let's double check. Do we only include -1 to the n when alternating series does not work? Do we only conclude the alternating mechanism? No. I mean, what? No, the answer is I would remove the phrase only. Meaning, go back, this whole term here, if this was the original, if they gave you this, let me go back. If they gave you this portion in section 12.2, okay, by section 12.2, which has the test for divergence, this limit portion here, what we just showed, does not exist. So I would remove the phrase that you have there to say only. Do we only include when this thing does not work? No, you include the whole series, meaning this is what an is, right? An is -1 to the n, 3n over 4n minus 1. You include the whole thing. I mean, that portion. It's a series, but you're including this portion that describes your series. It's the whole thing. So I took the limit of the whole thing. And that limit is really plus or minus 3/4. And this is a very clever thing that when you are in the alternating series test mode and it has to alternate, and you see that that's not 0, then what you can use is this test for divergence, and absolutely right. So Marbella was right. By the divergence test, you can show this thing diverges. So would it always come out with a plus or minus answer? The divergence test will always be, the divergence test, Kirby, is a test for divergence. It doesn't give you anything else. It doesn't give you convergence. It's just a test for divergence. So we can see by this test, it's a divergent series. And there you go. So yeah, so this is why I wanted to get to things like this, because of the fact that this is probably one of the more interesting things that shows up for the alternating series test. And, it's interesting. Anyway, we can kind of see a few more examples, I guess. Let's give you an example here that has n cosine n pi over 2 to the n. Okay, so we have this kind of nice example, n is 1 to infinity. Now, this is in the alternating series portion, because right here, cosine n n pi. This is an alternating mechanism. It alternates. So that the Bn portion would be n over 2 to the n. Now, here's something that I want to remark about, right? Notice that the numerator term is increasing. N is increasing. Oops. So we have an increasing in the numerator. We have increasing in the denominator. So they're both increasing here. Increasing. However, which one's increasing faster? Is it the numerator or the denominator? Exponential growth, ladies and gentlemen, is the fastest growth. Nothing grows faster than exponential growth. You know, n is 1, it's 2. And then n is 2, it's 4. And then n is 3, it's 8. And then n to the 2 to the 4th will be 16. And then 32. And then 64. So my denominator is growing much faster than the numerator. What this means, though, is that Bn will be decreasing because of the fact that 2 to the n is much bigger. And it's going to get bigger faster. And I think that's true for all n, though, right? N is 1, n is 2, n is 3. So the ratio there, we have a decreasing term for Bn. Now you say, why do I know that? Because I can then use, since I have an alternating mechanism, I have Bn that's decreasing. That's the first thing that we have to satisfy. So we know that. And then we can also now take the limit now. So the limit of now Bn, not An. This isn't the test for divergence. The limit of Bn is n over 2 to the n. Now, this looks familiar to me from what I did for you guys in those videos, right? If you guys recall, I mean, you look at this, you say, oh, Mr. Judge, that's infinity over infinity. I'm trying to take that limit. And I said, okay, look at this as a calculus question. X goes to infinity, and you have x over 2 to the x. And you say, I still get that. I know. But by L'Hopital's rule, I have to differentiate both of these. And this derivative on top is 1. And then you say, well, what's the bottom? Well, it's 2 to the x, I believe, natural log 2. It's a constant. So double check to see if I'm right about that, because, you know, it's been a long time since I've taken calculus 2. And so there you guys go. 2 to the x, natural log 2. Now, where does this go? This limit equals 0. So as you guys can see, a lot of those questions that I went over on those particular, this is a constant natural log 2, that I went over for you guys are important because they just pop up. So if this limit is 0, that means that this limit is also 0. And we know since both of these are now satisfied, we can now say here, by the alternating series test, we have convergence. And that's important for us. You know, so it's good to see some of these problems show up for us. Very interesting. Let's kind of look at this other sort of situation here. Here's another interesting one we want to be prepared for, I guess. Right? They're going to give us a question like this. Series 1 to infinity, -1 to the n, and we get square root of n plus 1 minus square root of n. And you look at this and you say, oh, I got an alternating series. And you say, why do I know that? There's your alternating mechanism. So it alternates. So my Bn term, here's my Bn, square root n plus 1 minus square root of n. Now the question is this decreasing? And the answer is, what you can do is you can now, if you like, use calculus. And you say, oh, okay, do I have to use calculus and say f of x is square root x plus 1 minus square root of x, and use sign analysis on the first derivative? And you might, although algebraically, I want to show you something. This is probably something some of you guys know already that you can do. Maybe you can say, okay, I'm going to multiply by that plus square root of n over, we're going to do a little algebra here. So this gives me n plus 1 minus n over square root here, n plus 1 plus the square root of n. And so my Bn becomes 1 over square root of n plus 1 plus square root of n. So this gets a little bit clearer because, which we know, the denominator down here, this is increasing, right? Meaning the square root of n plus 1 is increasing, the square root of n is increasing. Both these terms here are increasing. And so when you add them, they're also increasing. But then you say the reciprocal of this means that the whole thing, right, the whole fraction, is decreasing. And that's what I need. So I notice here that Bn here is decreasing, this Bn. Okay. And then you say, well, what's the limit of Bn? Well, the limit of Bn, I can use the version I just showed was equivalent. That's easier to take the limit now. Okay, because if I wanted to take the limit up here, you guys will see that that limit will give you an indeterminate difference. If I try to take the limit of that Bn, of the difference there, we get infinity minus infinity, and this is the algebra you would do anyway to fix it. Remember, if you have an indeterminate difference, so you do this kind of algebra. Anyway, this means that this limit is 0. And the denominator goes to 0, both of them. It's a sum, and so, the denominator goes to infinity. Both of them go to infinity, so your ratio 1 over this very, very big goes to 0. So this is what we're saying as n gets big, right? You do know square root of 1 gets big. Square root of n gets big. The sum gets big, but the ratio goes to 0. Right? So that's how you evaluate those limits. And then you can say here, by the alternating series test, we have divergence. So there's a lot of different kind of illustrations we could look at that are interesting for us. But I want to kind of throw not a curve, but I know where we're headed. And so where we're headed is that they're going to ask you, they're going to give you some of these things without without like a context, meaning how would you handle something like this? This is my point. They're going to give you something very simple. -1 to the n, and I'm going to say this will be e to the n. And you say, oh my God, what's this going to be? And let's do this. Let's say n plus 1. So you say, oh, is that going to be e? It is. Minus e squared plus e cubed minus e to the fourth, and so on. Okay? And the point is, it's alternating because you have this alternating mechanism, right? AM for alternating mechanism. And then you have an issue. And you might say, well, what's the issue? Right? I'm going to say to you, can you use the alternating series test? Can you do that? So what do you guys think? Can you do that? Can you use the alternating series test? And the answer is a big no. Because of the fact that Bn is e to the n, and this is actually increasing. So what do? It's an alternating series, but Bn is actually increasing here. How do you handle that? That's right. So I think, yes, Marbella, I think we do. I'll double check the schedule. We'll check it together, right? It's not decreasing. Exactly. This is not decreasing. That's right. This is increasing. So what do you do in this case? It's increasing. I'm going to say to you, think of it this way. Throw out the alternating series test because it simply does not satisfy the criteria. If you're going to use that test, it's an if-then statement, right? If P, then Q. You don't satisfy the assumptions. So because you don't satisfy the assumptions, ladies and gentlemen, you're not using the alternating series test at all. So you throw it out and you go, okay, if I throw that out, what's left for me to do with this? Go back to the homework you did on series, that first video I keep preaching about. So you're going to consider this whole thing as, get rid of the alternating mechanism. This is AN. The whole thing is AN. In other words, I'm saying to you, think of this as -1 to the n plus 1 e to the n. So when I take the limit of AN, which is the limit now of -1 to the n plus 1 e to the n, as that n gets big, what you're going to see here is that this goes to, you say, what does it go to? It goes to plus and minus infinity. You say, why? Well, e to the n gets big as n gets big. Is that right? And so if you include now the alternating component together, that limit goes to plus or minus infinity. Well, what does that mean? That does not exist. You can't go to two places. I mean, you can. This certainly did. But the answer is it's going to plus or minus infinity. It's exploding in opposite directions based on the value of n, because e to the n, here's the key. Because this portion here goes to infinity, the alternating part makes it go to plus or minus infinity, which means this limit of an does not exist. And now here's the conclusion. Here's the point. I want to end with this. By the test for divergence, this original series they gave us diverges. And that's the bottom line. That's what you care about. So ladies and gentlemen, yeah, they're going to give you some questions like this where you might not even, you can't even use the alternating series test. But don't conclude it diverges by the alternating series test, because the alternating series test is a criteria for convergence. You have to look at the whole thing together to see that this limit does not exist, which means by the test for divergence, the series diverges. And that's the rationale. I mean, and that's how you guys want to look at all those things, okay? And yeah, let's double check. So anyway, I wanted to end with this example because it's going over this very powerful and important test that you see that we'll be using. And if I go to my browser, and remember, I keep preaching about these. Hopefully you guys look at this. I know the last one has about 15 views, so I would have been comfortable if it had 50. But if we look at that schedule for Calculus 2, let's double check. And 262 schedule. It looks like, our next test is going to be June 1st, whenever June 1st is. So today is the 18th. Right. So, it's all the way down here. Anyway, I don't know. Maybe. Yeah. So Marbella, I think it would be better if we had our test on Tuesday. But anyway, it's in our schedule this way. We'll figure it out. But as you guys can see, what would be on your test, without a doubt, is definitely, these particular kinds of questions, series and sequence, right? So let me give you guys some homework on this section. Hopefully you guys get my announcements. This is section 12.5. And I'm just going to say you guys are going to do 1 to 20 all in these. And I just want you guys to note that in one of them that I can see here, you get sine of n pi over 2 to figure out what that kind of means. So maybe, I don't know, we'll see. Maybe I'll see some of those myself. So yeah, Marbella, it looks like we did have a factorial. Oh, it looks like we have a couple of them. So when Marbella asked about the factorial there, maybe later I can do a couple of these more for you guys. Yeah, so Marbella, it looks like there might be a few there, so I might even try them for you guys later and put them up for you. Okay? So we have a couple of those factorials there. We'll try that out. It's just going to have that. It's going to be, we'll see how that looks. Okay? So you're right. There might be a few. So I might do a couple more later and post that up for you guys as examples. It probably won't be very long. I might do about 3 or 4. And anyway, so look out for that. But yeah, looks like this is where we're at. So if you guys have any questions, concerns, see me during office hours. I hope you guys enjoy the alternating series test. I know I did. And study these series. And like I said, from my past, I have students do very well with this portion because it's kind of a new portion of what you're doing in some ways. But yeah, anyway, they do very well. But hopefully you guys will be a part of those groups of students that do well with Chapter 12. So stay safe. Keep working. I'll try to get a few of those up for you, Marbella, and everybody else, and we'll see how this goes. And yeah, tomorrow we're going to do 12.6, and that's going to be start with the ratio test, and then you have a root test, and those are the last 2 tests. There's only 2 tests left. But okay, see you guys tomorrow. And it's raining, so I guess we're not going outside, but, stay safe anyway, okay? See you guys tomorrow or during my office hours.